All right. Good morning, everyone. Let's just wait for a couple of more minutes because there's still some activity of people joining us. So let's wait another minute or two. Meanwhile, I want to share a poll with you just to get some idea of your Python knowledge. And now my poll vanished. I'll have to do that again. Inconvenient system. Okay. So let me start a poll. It would be helpful if you would enter this, then I have a better idea of your skill level and how to proceed here. Okay, so that looks quite good. With the majority of you being familiar with Python, many of you with a lot of experience, and some who know the basics, but no one who doesn't know Python at all. Okay, excellent. That gives me some idea. So let's get started. I'm going to share my screen. That's the most convenient way of doing this. All right. And let's start with a few practical things. So I sent you a link to this document. That is just a Google document thing, and it contains the practical information about this course. So you can find up-to-date information in this document. I will add things to it. Actually, just this morning, I added a note on certificates because I got at least 2 questions about this. So yes, you will receive a certificate. And for that reason, it's important that when you enter the system, that you use your full name so that I can actually identify you. If you didn't do so now, don't bother. I mean, it's just for the next sections. I will assume that you're here right now, so no worries about that. Okay, another thing which is useful is, of course, the training materials, and those you can find in a GitHub repository. So the link is to this particular website, which links to the GitHub repository, and there you can find lots of things. So one of the things you can find is the presentation which I'm using. So that's available there, PowerPoint. And what you will also find is files that define the environment, the software environment, which is required to run the source code. And of course, the source code is also there in the source code directory. No surprise there. And There you will find Jupyter notebooks and Python scripts to illustrate many of the things which we're doing here, and also some additional stuff which we probably won't have time to talk about. So that's available as well. I'll put the link to the Word document again in the chat. Normally you have it, but just for convenience. And of course, in there you will find links to the other materials. Okay, so a few other practical things. Please, let's make this as interactive as possible. That's nice for me, because then I know how you are feeling about this, whether I should speed up or whether I should slow down, whether I should explain things more clearly, whatever. So please feel free to interact. We're not that many, so I'd say if you want to ask a question, you can just activate your microphone and ask it, no problem. On the other hand, you can also use the chat. I've arranged my screen in such a way that typically I can keep an eye on the chat, so normally I'll see your messages. It's most convenient if you message to everyone, so not specifically to me, because I typically keep an eye on only one chat channel, because that's the only thing I can. I can only watch one chat channel at a time, and that is the one which is sending messages to everyone. Another practical thing is I'm recording these sessions. Now, there is, of course, a GDPR thing, because your names will be visible in the recording. So that means that without your express permission, I can't share these recordings. So at some point, I'll ask you to indicate whether you're okay with sharing the recordings. If not, you should let me know. But I'll do that officially using some email or something like that in order to ask your explicit permission. Okay, I think those were the practical things. Are there any questions at this point? Apparently not. Okay, excellent. So let me move to my presentation, and let's switch this thing to presenter mode. And let's increase this a little bit. Okay, that's about the maximum we can get. All right, so let's get started. So this link was already mentioned. This is just to the repository, so you have that. Okay, so in the slides, I use a few conventions, and basically they're just to make things clear. So if something happens on the shell, and that would typically be a bash shell, a Linux bash shell, then it's rendered on a black background. And you will also see a prompt here, which basically means don't type it. It's a shell command. So that's just to represent and to emphasize that it's a shell command. If something happens in the Python shell, then same convention, but with a triple larger than signs for that particular prompt. And the same for the IPython interpreter, then we would have something like this. I don't think there's much of this in the slides anymore, but nevertheless. More importantly, if there is code or file names or something, and that's in line, so in ordinary text, I emphasize that using a monospaced font, which is, well, okay, somewhat ugly, I would agree, but still it is useful to distinguish. Longer code fragments are typically on a gray background, same ugly font, and data files are on a yellowish background, so to distinguish them from source code. And what you will see fairly often is this ellipsis, these triple dots, and that just means that there is more code or data than I could possibly show on that particular slide. But normally, either it's very easy to guess what should be there, or it has been explained on a previous slide, or it will be explained on the next slide. So typically, the information is there somewhere, So you should be able to figure it out. Okay. So in general, let's do some introduction thing. Out of the box, of course, you can use Python and you can do many things which are interesting and useful and so on. But as you know, Python is an interpreted language, and Python is not the fastest interpreted language. So in general, interpreted languages are slower than compiled languages. But Python for an interpreted language is even considered slower than other interpreted languages. So is that a problem? Well, it depends. So that's quite okay for a one-off, a program that you run just once. If it doesn't take half a month, it's kind of fine because, yeah, who cares if you only run it once? It's also fine for prototyping. I often do a prototype in Python, even if I know that at the end of the day, I will have to re-implement the code to get it run faster on HPC systems. But still, it's useful to have a prototype as a baseline. Then you can easily verify whether your algorithms are fine, whether the idea you have is correct, with less effort. And of course, then later on, you worry about performance. Also, if you run your script and it just runs very briefly, let's say a few seconds or something like that, okay, do you care? Well, unless you run it a million times, probably you don't. So it's not necessarily a problem. Of course, it is a problem for computationally intensive tasks. So if you do a lot of mathematical computations, and that's typically what you do in an HPC setting, then using Python out of the box without any consideration is not necessarily the best idea. And that's most likely why you're here. So let's quantify things a little bit. Let's consider this code, and it's two functions. And the first function init matrix is going to, well, initialize a matrix. And as you can see, the matrix is represented as a list of lists. Okay, nothing special happens. We use the random module, which is in the Python standard library. As such, no problem. Second function, matrix multiplication. So we get two matrices A and B, and we compute the matrix C, and that is just the matrix product. And the formula is there, which you will remember, obviously, from your courses in mathematics. Okay, so let's run the code, and let's do that for 500 times 500 matrices. So that's not that large. And the first function takes about 1/10 of a second. And the second function, matrix multiplication, takes 32 seconds. Okay, what's your gut feeling about that? Especially about the 32 seconds. Do you think it is okay? Do you think it's a long time? Do you think it's very fast? What's your gut feeling? No gut feeling. Okay, let's compare. Let's do the same thing in C and in Fortran. And if we do the same thing in C, you see that the time to matrix multiplication goes down considerably. It's half a second in C. And the implementation is the same. So basically, initialize matrix does similar things. The matrix multiplication is also multiplied with the same form, well, implemented using the same formula. If we do that in Fortran, you see that we get down to, well, a little more than 1/10 of a second for the matrix multiplication. So yeah, clearly Python is really, really slow. Why is this so horrible? Of course, we already mentioned that it is an interpreted language. So yeah, that doesn't help. But the difference is really, really huge. So what else is going on? Any ideas? And of course, I'm mostly interested in the multiplication thing. So if you look at the inner for loop, and that's of course where the work is happening, and then you see that what we're doing is we're taking a matrix element, we multiply it by the element of another matrix, and we store that into a third matrix by adding it. Yeah, true. So that would be a multiplication. So the matrix has been initialized. That is, well, the matrix has been created. So the only thing I'm doing is assigning elements. So that is a thing. But if you look at the code and you think a little bit about Python, because that's important here, then you notice that the matrices are not matrices in the sense that we use that concept in mathematics. Because in mathematics, obviously, a matrix is a data structure that contains the same type of elements. All elements of a matrix are, for instance, floating point values. And that's not the case here. Well, it is the case here, but the Python interpreter cannot know. A list in Python can contain anything. I'll discuss that later if you don't mind. So whether C is why C is slower than Fortran? Yes, there is a reason. There is a good reason. I'll talk about it in a minute if you want. So let's first consider the inner loop a little bit. So basically, a Python list can contain anything. So if we break down that statement in the 4k in range loop, then what happens? We have an object A, and we apply a square bracket operator to that. So basically, can that happen? Okay, we should test. Then we use I as an index. Okay, so can we use I as an index? Yeah, because it's an integer, but we need to check. Another thing we need to check is whether I is within the bounds of the list index. So basically, whether it is between minus the length of the list and the length of the list minus 1. If that's the case, we can proceed, but we need to check. So we have AI now, but we already did quite a number of tests. Next, we apply the square bracket operator to that. Okay, can we? Yes, because AI is a list. Can we use k as an index? Yes, because it's an integer. We need to check the bounds. Okay, same story for B. Then we have two things and the multiplication operator. Can we multiply? Yes, because both are floats. Okay. Then, same story for C. Then we have to do an addition. Can we do that? Yes, both are floats, etc. So you see that due to the fact that we represented our matrix as a list of lists, the Python interpreter has to do many, many tests in order to verify that what we are doing is in fact possible. Because a list can contain anything, and any list element has to be checked at runtime. So that's why Python is really, really, really slow for that. Okay, so there is a very good remark which Caesar is making, that indeed there is such a thing as row order or row major versus column major, indeed. So that is indeed a concern. But for the matrix multiplication here, in this implementation, it doesn't matter that much because one of them is always going to be wrong. Either A or B will be accessed the wrong way around. So there is a lot to say about the matrix multiplication. And a lot of research has gone into it. And as a matter of fact, it is still subject to active research. I think in 2020, in 2020, a very interesting paper was published on it. So yeah, there is a lot of things to say about it. Okay, maybe a little bit about C versus Fortran. Why is Fortran faster? Well, I can make, with work, I can make C as fast as Fortran. But a naive implementation in C has problems with respect to optimization. The problem is that if I pass two arrays to a C function, the compiler may not assume that those arrays do not overlap. Okay? That is possible in C. That is completely forbidden in Fortran. Hence, since it's forbidden in Fortran, the compiler can make the assumption that the arrays passed to a procedure are distinct. And it can do much better optimizations, including vectorization. And that is not possible in C without help. If I'm using C99, I can use a restrict keyword, and that means that I assure the compiler that the pointers, because arrays in C are just pointers, that the data the pointer is pointing to will not overlap. And then the C compiler can do the same optimizations as the Fortran compiler, and you get comparable speeds. You get that out of the box due to the design of the Fortran programming language. So that's why. Okay. So basically, the answer or the solution to the problem that Python is that slow is that we should actually use libraries. And one important library, which many of you will be familiar with, is NumPy. No, we can't, unfortunately, because Python is not going to compile, so it's not going to do that factorization. However, we'll see later how we can actually speed up things considerably and get around this kind of problem. But that's for later. Okay, so you're most likely familiar with NumPy. So what it gives you is data structures for arrays. And basically that means that you have proper data structures where the library ensures that you have a single data type in an array, and hence it has been also compiled with optimizations, with factorization switched on, etc., etc. So basically, you actually get very good performance because under the hood, it is using BLAS, a good implementation of the BLAS, basic linear algebra subprograms, and that library will actually ensure that you get good performance. We'll discuss this in a bit more detail later on. There is also Fourier transforms, mathematical functions defined on arrays, and so on. Also pseudo-random number generation, simple statistics, and so on. And of course, there's SciPy for more mathematical functions, but especially for things like linear algebra and also dense and sparse linear algebra, solving sets of differential equations, and so on. So these are typically your go-to libraries for scientific programming in Python, and using those can already speed up your computations considerably. And of course, if you're into data science, you would actually use pandas. Okay, so don't reinvent the wheel. Certainly don't implement your own matrix multiplication, because really, as I already mentioned, there have been decades of research. Unless it is your research field, you don't stand a chance to get a decent implementation. Well, you will get a decent implementation, but not one which is as fast as the typical libraries you're using. Okay, so let's use NumPy and time again. So the implementation simplifies considerably. And if we time it now, you see that the NumPy implementation for init matrix goes down to 1/10 of a second, comparable with Fortran. And if you look at the matrix multiplication, you see that it goes down to 0.77 seconds. 0.077 seconds. So this is even faster than Fortran. That's kind of neat, isn't it? Okay, so if we make a table out of that to summarize the results, then you see that from the naive implementation in Python and Python using NumPy, we go down by a factor of 415, which is a number I would call, well, pretty spectacular. And as you can see, the naive Fortran implementation is a bit slower than the NumPy implementation. However, I'm a big fan of Fortran, so actually if I use the same libraries as NumPy is using with Fortran, then it's even a little bit faster than, well, a little bit, some percentages faster than Python and NumPy. So the trick under the hood is to use the right libraries, both in Fortran and in NumPy. Okay, so one of the things which you get out of the box when you use NumPy, and this is something you perhaps are not really familiar with, is NumExpression. And that's an additional library which works on top of NumPy and improves things here and there. So it may speed up your computations, which is a good thing, and it can also conserve memory, which is another good thing. So one of the things it can also do is under the hood use Intel's VML library. So you might not be familiar with VML. So that is a vector library in which Intel has implemented, and especially for short vectors. So for instance, for vectors of length 2, vectors of length 3. So the typical vectors which you use in order to do transformations, graphical transformations, things like that, and linear algebra on small systems. And that also means that since the VML library is implemented using multithreading, so basically it can exploit multiple cores on your hardware, that actually you get that for free. It's automatic since the VML library uses multithreading. So that's quite nice. There are some restrictions on what you can do. So it's only for element-wise operators. The trigonometric functions and their inverse can be used. Things like logarithmic and exponential functions, square root, and so on. The where and accumulation with sum and product. So these are the things which NumExpression will speed up. So how does it work? Let's have a look at, for instance, a where operation. Okay. So basically, we import NumExpression as NE. We also import NumPy as usual, and we create a 1000 by 1000 matrix somehow. Okay, that matrix is A. And now we are going to use NE evaluate. And what it takes as an argument is just a string. And that string is a NumExpression expression, in this case a where. So we will create a new matrix which has two distinct elements, 1 and -1. It will have an element 1 in every position where there is an element larger than 0.5 in the matrix A. If the element of A is less than or equal to 0.5, it will have -1 as a value. So masked is going to be a matrix with the same dimensions as A, but with values 1 and -1 corresponding to the positions, to the equivalent positions in A. Okay, so of course you can also happily do that using NumPy. There is the where function in NumPy, so I could do the exact same thing in NumPy. If you do that on a single core, then actually this is 10% faster than using the corresponding NP where. Okay, 10% is kind of neat. Another example is arithmetic. So basically, I have, in this case, 3 matrices, A, B, and C. They have the same dimensions. And I'm doing an element-wise multiplication of B with C element-wise raised to the power 3. So remember, in Python and in NumPy, the star operator is element-wise. The power operator is also element-wise. Yes, I'll talk about that explicitly in a couple of slides. So why is this useful? You might wonder, because of course I could just write D is equal to 3 times A plus B times C to the power 3. And of course I would get the same result. But this is faster. Why? Because special code can be generated which takes into account that this is all element-wise operations, and that at the end of the day, I can do the entire evaluation of an element of D completely element-wise, so with only the corresponding elements of A, B, and C. And this, of course, allows for quite a speed up. Also, and perhaps more importantly, it also saves memory. Because if I'm just evaluating this expression as a NumPy/Python expression, yeah, then what's happening? I'm creating a new temporary array to store 3 times A. I'm creating a new temporary array to store C to the power 3. I'm creating a new temporary array to store the element-wise product between B and that temporary array. And only then I'm computing D. So basically, in flight, while this expression is being evaluated, if I don't use num_expression, but Python and NumPy straight, then a lot of temporary arrays are floating around. And of course, if these arrays are large, then I'll have large temporary arrays, which is not necessarily what I want, because I might run out of memory. So basically, the speed up here is pretty impressive. So just on a single core, it's 20 times faster than NumPy. So if you have NumPy expressions that are element-wise, it definitely pays off to have a look at num_expression. Okay, so there was a question about Intel distribution for Python. Is it worth it? I would say yes, it definitely is, because you are sure that you get high-quality libraries. Now, if you use Conda, then actually, typically you get good libraries. Maybe I can show you. Okay, let's increase the font size, and let's make this a little bit larger. And then we have some more screen real estate. Okay, so let me go to the So this is the repository, which you also have access to and which you can clone from GitHub if you want. Let's increase the font size a bit more. So you find many things there. one of the things which you do find, well, two of the things which you do find is environment.yaml and this Python for HPC Linux 64 conda specs text file. Both of them allow you to create an environment which you can use in order to run most of the things for this training. Typically, to deal with Python environments, I will use Conda. There are alternatives. You've got Mamba, you've got Poetry, and so on and so on and so on. So there are many options. You can also use pipenv, etc. I started using Conda at a time where there was not much alternative, and I'm pretty happy using it. So yeah, I don't see a compelling reason to switch for me. Okay, so what Conda environments do I have? I have Python, and normally I should have Python for HPC as well. Yes, I do. So I can activate it. All right, so the Python version itself is probably somewhat older. It's a 3.8, reasonable, not very recent, but okay. And what is important, and why I'm showing you this, is I want to show you what is installed. And that is something to keep an eye on. So basically, as you can see, lots of stuff, nobody cares. But what I do care about is this here. These lines. These are important. And the next line is also important. Well, the next 3 lines are also important. But let's start with this one. So basically, MKL is a library which has been developed by Intel, or which is being developed by Intel, and the name is Mathematical Kernel Library, hence MKL. And the nice thing is that Intel makes it available as a runtime for Conda environments. So this is just the default Conda channel which I'm using, so nothing to do with Intel. So this is good. If you have Conda environment where you have the MKL, then typically you're good with respect to performance. You might also have an environment where you have OpenBLAS. OpenBLAS is also a good implementation of this basic linear algebra subprograms library. So that would also be okay. Typically, you're happy with MKL. It gives you good performance, and Intel has done a really nice job on it. The next few lines are not relevant right now, but they will be relevant later on. So that's MPI, Message Passing Interface, and that's your communication library. And this is something I'm not happy with. Well, I'm okay with it on my system because this is just a single node and it's a desktop system, and basically I can do NPI on it, and I don't particularly care about performance here. But I would be very unhappy if I were using that on an HPC system, because this is going to give you bad performance, for sure. And that's actually why the Intel implementation is a good idea, because besides MKL, which you kind of already get for free, it also contains a library for Intel MPI. And that means that even with a Conda environment, which is not specifically built for your HPC cluster, you still get very good performance for MPI, and of course also for the scientific libraries like NumPy, SciPy, sklearn, and so on and so on. So that's kind of good to know. And installing the Intel distribution is quite easy. You just do conda install with the Intel channel specified. And I think this needs to be a single dash, not a double dash, but okay. So basically, this would give you the Python interpreter, and it would also give you all the optimized libraries, which Intel spent quite some time on. So basically, yes, that's a very good idea. So there are some NumPy optimizations, for instance, with respect to generating random numbers. MKL contains quite some libraries. Well, contains a library to generate random numbers, and you might be surprised, but that's a pretty slow process. So if you have code that really generates lots and lots of random numbers, then this will actually help performance considerably. There is also thread scheduling with TBB, so threading building blocks, which is an alternative to OpenMP. We can discuss this when we talk about multi-threaded coding, but this is also a fairly important one. And then there is, as I already mentioned, Intel MPI, which is used for MPI for Pi. We'll discuss that later on as well. But that would give you good performance on an HPC cluster, typically. And for those of you interested in machine learning, so scikit-learn, which is your typical go-to library for all classical machine learning algorithms, that is optimized as well in a library which is called PyDAL. What is DAL standing for? Data analytics, something which I forgot, but basically it contains a number of optimized libraries for dealing with data analysis. Okay. Any questions about this before we continue? All right. Another thing you can do, but it's somewhat tricky, is using PyPy. And PyPy is just another implementation of the Python interpreter. So your typical Python interpreter is CPython. Don't confuse that with Cython, which is a different thing. CPython is just the C implementation of the Python interpreter. Because yes, indeed, the Python interpreter is in fact implemented in C. Okay. There are some problems with the CPython interpreter. That's a different topic. We'll also discuss that when we discuss multi-threading. But it's also, for other reasons, somewhat slowish. And that's why people develop PyPy, which is a different interpreter, and it does just-in-time compilation. So it will give you better performance on condition that your program runs for quite a while. If you have a Python program that just runs for half a second, even if you run it a million times, don't use PyPy. Because the first thing that PyPy is going to do is a compilation step. That takes time. So unless your program runs for a considerable time, that gain which you have by this just-in-time compilation is really not going to help you because the compilation also takes time. So that's something to keep in mind. Another thing is that, of course, it will only substantially help when the heavy lifting, the computational heavy lifting of your application is in fact written in Python. So if you use a lot of NumPy or SciPy, then yeah, you're not going to gain that much because those libraries have been implemented in C or in Fortran or in whatever, and are not going to benefit from PyPy. So there is a list of modules which it actually supports. So the list of compatible packages is, let's say, work in progress, and you can have a look at the things which are supported. So for instance, yes, you can use NumPy, but you're not going to benefit from using it. in the sense that PyPy is not going to make that particularly faster because the optimization is done in a library which is opaque with respect to PyPy. PyPy can't see into it. Also note that typically PyPy is considerably behind the Python development curve. At the moment, Python 3.10 is the latest. Python 3.11 will be released in autumn. So 3.5 is really, really old. And there are quite a number of features which I would dearly miss if I were to use Python 3.5. So yeah, I would say use with care, and certainly first check the package list, whether what you want to use as modules, as third-party libraries, is in fact supported by PyPy. It's really important. You may get considerable speedups, though. And of course, it's a free lunch. The only thing you need to do is to run your Python script with PyPy rather than with the Python interpreter, the C Python. Okay. So, num expression, there is documentation on it, obviously. And this is essentially what you get for free. So out of the box, without doing any effort, you can get some considerable speedups already using num expression on the one hand, using the Python interpreter, which Intel provides, and perhaps if your problem matches it, using PyPy. Okay, any questions about this? So one of the things I suggest you try, not right now, but maybe later today, is to do a little comparison experiment. Create two Python environments, one with the standard Python interpreter, standard Python distribution, and another with the Intel distribution. And if you have some NumPy intensive code lying around, just benchmark and see whether you notice differences with respect to performance. And that would definitely be a good experiment to do. Okay, the next topic I want to discuss is profiling. Because, yeah, we're done out of the box with no or very little changes to our code. So, yeah, it's still too slow. One of the things that you should really not do is look at your code, maybe make a print of it, and staring at it and saying, okay, I think that I should change this part of my code in order to make it faster. That's an approach which is unfortunately very often taken, but it's not a good one. So don't optimize blindly. It's a waste of your time, especially since you may have some intuition about what is taking time in your computation, but often that intuition is not really accurate. Especially with Python. Python is, in my opinion, a very difficult language to reason about performance. Very often it's really counterintuitive. Let's have a look at the following somewhat silly example. Let me start a Jupyter notebook. Maybe a short note on my setup. So as you probably noticed, I'm using Windows. To be precise, I'm using Windows 11 as my main operating system. Basically because, well, okay, I need to write Word documents, I need to make PowerPoint presentations, all that kind of, let's say, office kind of applications. I also like photography a lot, so basically I need Lightroom and so on. So yeah, that's why my desktop system is just a Windows machine. Okay, but of course I don't use Windows for scientific computing because, yeah, that's not really a good match. So I need Linux. Now, typically, you have a number of options to run or to get something Linux-like on your Windows machine. And I would say, classic approach is using virtual machines. You have several options for that. So one option would be Oracle VirtualBox, which is a very nice product. It's for free, made available by Oracle, and it works really, really well. So that's one option. Another option, which is what I typically use, is VMware, and that's also very nice. I have VMware Workstation. That's a paid license. You can also use VM Player, which is freeware. That's also very good, and I do quite a lot of my scientific computing in that environment. I'll probably fire it up at some point. Just now, I don't think I have it running, and I don't want to start it running. So that's your second option. Yeah, under the hood, this is what we're going to do, is using Hyper-V, because in modern Windows, let's say starting from Windows 10, you can use WSL. I'll put that in the chat. And specifically use WSL2 if you have the option. That's Windows subsystem for Linux. And that's what I'm running here. So what does that give you? Well, it allows you to install a Linux distribution. You have a few options. One of them is Ubuntu. There are a few others. Oh, for the life of me, I don't remember which distributions. I think Kali is one. Kali is one which you would typically use if you're interested in cybersecurity, because it has a lot of stuff for testing applications, for hacking, for intrusion detection, things like that. But typically, I would use Ubuntu. So the Ubuntu which you have available is a 20.04 LTS, so one of the long-term support distributions, which is not the newest one, because at the moment, I think we're at 21.10, if memory serves. So it's behind the curve a little bit, but for scientific computing, typically, it's okay. So that allows you to run a bash shell, which I'm doing here, as a Windows application. If you have one of the latest builds of Windows 11, you can actually use X11 applications. So basically Linux applications with a graphical user interface. But then you need a recent build of Windows. Okay, so this is WSL, and I'm going to run Jupyter Lab. Jupyter Lab I have as part of my Corona environment, and you might be a bit surprised that I use the --no browser extension, but option, but that is just to avoid an error message, which I would get because Jupyter Lab would try to start a browser, and I don't have a browser installed in this Linux distribution. So I'm just starting the backend, and I can just Control-click, and it will launch a Windows session. Okay, so let's reformat this a little bit. So this is actually pretty neat in a way, for some definition of neat and some definition of weird, in the sense that the kernel which I'm using is running under Linux, which is emulated on Windows, and the browser which I'm using to interact with that kernel is a Windows browser. So that's kind of interesting. Let's phrase it that way. Okay. So basically, if you use a Mac, you have a command line, you have a terminal, and you can use anything you want. I'm not really familiar with Mac OS, so I can't tell you which browser works best. Probably Chrome would work quite well. Firefox likely also. I'm not sure about Safari. I really don't know whether it works well with notebooks. I can't tell you because I don't have a Mac, so no idea. But typically, just use Miniconda. I think the installation instructions for Miniconda are listed here somewhere in environment. So here basically, this is the documentation, the user guide for Conda. And I would just say, okay, download Miniconda, install it, and you can create your environments in the on the terminal of macOS. That's probably your best option. Okay, let's start a notebook. All right, so let's consider a small example to show you that things in Python or reasoning in Python about performance is sometimes a little bit weird. Okay, I'm going to write two functions, and they're, let's say, inspired. Okay, excellent. And I have inspired by bioinformatics. Maybe reason to choose Miniconda over Miniforge. I don't even know Miniforge, to be honest. So if Miniforge is similar to Conda, there is probably no reason to do that. Well, to choose one over the other. So if you're happy with Miniforge, I'd say feel free. I didn't even know it existed. As I mentioned, I have been using Miniconda like forever, and I've never seen a compelling reason to switch to anything else. But I'll look into Miniforge as well, because it's always interesting to know and to see whether it has some features which are, well, which make me switch, which is always possible, but I don't know. Okay, so I'm going to write two functions, and they're going to count nucleotides in DNA. Okay. Okay, and I can do that in several ways. One way is that I simply say, okay, I have my nucleotides, and that is a dictionary, and for each nucleotide in the DNA string, I'm going to add one to my dictionary, and I'm going to initialize this. Do it a little differently because I'm getting bored here. So nucleotide, so nucleotide in ATG. Okay, it's easier. And then to update nucleotides. Okay, so this is one implementation. Let's see whether it does something reasonable. So A would be, I'll create a long one later on. Okay, that seems to work, and it seems to be correct. Okay, so that's good. Now let's do a different implementation. Okay, and I'm going to return a dictionary. Let's test that as well. And it gives the same result. Okay, that's reassuring. Now the question is, which is the fastest implementation? We'll try it out in a minute, but what's your intuition? Is count nucleotides going to be slower or faster than count nucleotides 2? What do you think? The second one is going to be faster. Why would that be the case? Yes, you are indeed right. So in a way, this is counterintuitive. Because if you look at the first code, so in cell 3, then actually you would expect it to be faster because you only iterate once over the string, while in fact in the second implementation in cell 5, you iterate 4 times over the string. So if you just look at the number of operations, then your intuition would say, okay, count nucleotides must be faster. But indeed, you're right. And all of you who said, well, okay, due to count, this is going to be faster, you're perfectly right. Indeed, the count function is implemented in C, and it will do this count really, really fast. So basically, let's generate some data. Let's import random. And let's create a long DNA string. Okay, so I've got the long DNA string, and now let's time. Yeah, nucleotides. It's DNA long. So for those of you who are not familiar with the time it magic, it will execute an expression many times, and it will compute statistically relevant measure for the performance. Okay, so let's do the same thing, but now for nucleotides 2. And then you see that indeed it is really considerably faster by a factor of about 7 approximately. So quite a lot faster. And indeed, that's due to the use of count. Quite right. But if you're, say, teaching programming to people who well, start out, then this is very annoying because you have to explain these kind of implementation details, and that detracts a little bit from the actual message, from the actual number of operations which you would like to perform. Okay, so this was just to illustrate that sometimes intuition can be wrong. So one of the things you can do is micro benchmarking, and that's indeed just what we have been doing. So using the time it magic in order to time particular functions, particular expressions. That's very easy, but the problem is that might lead to premature optimization. For instance, I might be spending time on a function which is not really my performance bottleneck. And then, of course, doing that is a bit a waste of time. So you should always profile with a profiling tool. And that's a little bit more complicated, but it will really identify the actual bottlenecks rather than having you guess what might be the issue. Okay, let's perhaps have a short break, just a couple of minutes, something like 5 minutes, in order to give you the chance to have some tea or some coffee or whatever. So break. Well, let's say 11:15. And then we'll continue with profiling. If there are any questions, feel free to type them in the chat. Yeah, the second version with the count is indeed the fastest one. So that takes only 7.8 microseconds on average, while the other one takes 55 microseconds. Yes, your guess was perfectly correct, indeed. Very well done. Yes, I realize that since I was not sharing the screen, you couldn't see the notebook. I'll share it again, sorry. Here it is. All right, let's talk a little bit about profiling. Now, both are useful. I mean, a profiling tool is quite useful, but also micro-benchmarking is useful. It's just a matter of context, and you should use them whenever one or the other is appropriate. So, timing functions, you can use either time or timeit, typically in IPython or in a Jupyter notebook. And basically that helps you to judge the performance of expressions in Python. So there is on the one hand the line magic, which is percentage timeit, and on the other hand there is cell magic, which is double percentage. So if you need or want to time longer code, you can do something like this. So double percentage and then some expression, some Python code, for instance. You might want to time how long it takes to define a function. That's also something the Python interpreter is doing, so you can time it, and then you see that that is actually fairly fast. Probably this is not really a correct result. That seems really, really short. So most likely this is skewed. Okay, anyway. So that's your typical micro benchmarking. The good thing is it's done multiple times. So basically it average over certain effects, like for instance, the CPU frequency varying over time, things like that. You can also use that from the command line. So by using Python and then -m timeit and some expression. This is really somewhat annoying, let's put it that way, because basically you have to make sure that the indentation is correct and so on. So that's a little bit a pain in the somewhere. So yeah, whether that's so useful, I don't know. Probably not that much. Okay, then let's switch to a profiler. So the Python standard library contains the C profile module. And the nice thing is you can run any Python script using this C profile module. So basically it means that the script will be run, but profiling information is going to be collected. And you do that by specifying the -m C profile option, which means run the script under control of the profiler. And then you can set a sorting criterion. In this case, I want to sort on time. And what you get in that case is the functions which are called in order of the time spent executing them. And then you see that in this case, the function primes is being called once, and the total time is this amount of time. You see some functions also get called multiple times. In this case, the function append for list is being called more than 1,000 times, and basically its total time is very short, but it's called a lot. And this function here, the string join, is called 43 times. It also takes a very short while. So essentially, if we wanted to optimize something here, that would be this particular prime function. Okay. It is very convenient to use cProfile, but to actually visualize it using SnakeFizz. So we run the application as usual, but we add an additional option, the -O option, and that simply says, okay, this profile is going to be saved in a file. And apart from that, it's the same as before. So the output file is going to be primes.prof in this particular case. And then we can visualize this using SnakeFizz. And this is in fact rather nice because it will open up a web browser, and this is also interactive. Let me perhaps try and show you. Let's see, I'll need another window. See source code. See, is this a standard implementation? Yeah, it did different things. Yeah, this is not really. I would need something that is nice to. But there is a Primes vanilla there. Yeah. Okay, so I can run this with the Python option. And work. How do not? Don't I find NumPy? Okay, yes, I forgot to activate my environment here. So that would be Python. Okay. Of course, this should run. Yeah, it does run. Okay. And probably I can also specify the number of primes. Let's make that a bit larger. Let's say that million. That's maybe over ambitious. Let's just check. Okay, so this is fairly fast. All right. So I want to profile that. So I would run it with Python, see profile, dash sort. Doesn't really matter. -O is profile off. Okay. And I don't care about the output, so I'm going to send that to null. All right. So now I've got my profile with some like who has SnakeFizz. I do. So that would be profile. All right. As you can see, I profile started. With the dash and flag. Okay. So how do I deal with command line arguments? Basically, what I use is, okay, let me shut this down for a second. Close it, and let me start pmux because otherwise, stopping that within 10 seconds. So let me show you the primes script. What I'm using typically is argparse to deal with command line arguments. And this is part of the standard Python library. So you always have it available. And it's a very easy way to get command line arguments in a Python script. So you create an argument parser, you may give it a description, and then you add the arguments to the argument parser. You do that basically step by step. So there's a positional argument, which is the implementation, and I can either have Python, Numba, Python array, or Numba array, whatever they are. And as a default, I specify Python. And I can have that either specified or not specified. That's what the question mark means. If it's not specified, it's going to be Python. Otherwise, it's going to be one of these values. I also specify some help for this option. And I also have an option -n. And as you can see, the type of this is integer, and the default is 10. Again, some help. And then I can get these options using argparse, parse arguments, and I can access them using this notation here. So if the implementation is something, then I do, otherwise I do other things, and so on. Okay. So that's what I typically use for command line arguments. Another very nice library for that is called Click. So it's a bit more modern. It's pretty cute, but it's not part of a standard library. And yeah, given that it's in the library, in the standard library, and that I've used it like forever, I'm just typically going to use argparse rather than Click, just out of habit. Okay, let's do the snake fits thing again. Right. So this is basically my profile, and as you can see, you read it top down. So this is the whole runtime, and then quite a while is spent in this primes3 module, as you can see, and then basically in prime vanilla Pi. And here you can see the actual functions which are being called and a breakdown of them. So this is a very convenient way of analyzing the information. Here you get the classic profile. As you can see, the number of function calls. You also see the total time, the cumulative time, and so on, and the per call time as well. And this actually can be represented as a sunburst as well. So basically same information, but represented slightly differently. Okay. So this is a very convenient way of analyzing what is going on in your function and what actually takes time. Okay. And you can activate the stack, etc., etc. I'm a little surprised because I would expect a pop-up here, and that doesn't seem to happen. So normally I should get the function. Ah, here they are. This is the directory. And the name. Yeah, here's the name. So basically, that tells me what is being called. Okay. So that's a convenient tool. So the call stack is inside out. So basically, the functions which are called deepest are here in this starburst furthest out. This is the total runtime here in the middle. Okay, so this gives you a visual representation of your performance, and that typically tells you where to look for opportunities for optimization. Obviously, the largest circle segments are the most interesting to try and optimize. Okay. Now, the problem basically is that that gives you information at the level of functions, but it does not give you information at the level of line numbers. And that may be much more convenient. because that will tell you where the actual problem is in your function. For instance, here we have this this prime function, and as you can see, now it's broken up line by line, and for each line we have the time spent on it, and basically the number of times the line is executed. Of course, in this particular case, all lines will be executed once, except for this one here, because if the Boolean is false in this particular case. But you see immediately that in this particular code, this line here, so the initialization of the Python array, is in fact problematic. That takes the vast majority of the time in this particular function. That's something we'll come back to later. But basically, the line profiler, which is an additional package, which you can install using Conda, gives you quite some extra information. And you run it similar to the C profiler, but there is an application to do it. It's called current-prof, and then you specify the options which you want. So basically, verbose, I want the verbose output, and I want the line output -L and verbose -V. And then you get this type of output. Okay, now one of the things that you should realize is that this really increases your runtime considerably. I mean, not by a factor of 10%, but rather by a factor of, like, say, 10. So this is really slow. So that means that you, for large application, it's just not feasible to do a line profiling. So there is a decorator which you can use in order to ensure that a particular function gets profiled, and that's here. That's this add profile decorator, and that tells the line profiler, leave everything alone, don't profile anything, except where there is this add profile decorator attached to a function. Okay, that's quite important. So basically, line by line, and show the profile on the screen. Okay. So okay, so the recording thing, as I already mentioned, yes, I am recording. I can make these recordings available if I get your permission. Problem is GDPR. So basically, your names are visible. I cannot distribute anything that contains personal information without consent. So I will at some point ask you to whether you have objections to this being made publicly available. If there are no objections, I'll just put it on YouTube and make sure that you get the links. They will be in the document, in the Google Docs. On the other hand, if someone does have an objection, we do it differently. I'll still put it on YouTube, but it will be unlisted. And then if you're interested in the recording, you just send me an email and I'll send you the link, which then you promise not to distribute. Okay? So that's the way we can deal with this. Yeah, I know, it's GDPR, can't help it. Okay. So optimization workflow, how do you typically go about? So typically I would start using cProfile, and then I know in which functions to look in order to optimize things. That would give me my hotspots. Okay, then once I know which function to concentrate on, either, okay, I have a good idea of how to optimize them. If I'm not quite sure, it might be a good idea to then use the line profiler to see which lines of the code in that particular function are really taking up much time. But again, remember, this is going to generate huge overhead. So take that into account. And then basically, you use the add profile decorator. I don't know why this is here twice, but okay. And then while you're trying to optimize things, you can of course use the time it benchmarking to experiment. Now, what's also very important here, and I really want to stress this is development. You're changing code that works. Well, at least you're convinced it works. So you're changing it. So you might introduce changes that break the code. Okay, that would be inconvenient. So you need two things in your development process. One of them is testing. So if you have a battery of tests that you can run and you can run them easily, then that's a very good thing to have, because you run your tests, you're kind of reassured that your code does the right thing. You make a change to improve performance, and you run your tests again. If the tests succeed, well, you probably didn't break anything. If your tests fail, you know that you broke something and you can immediately fix it. If you don't have these tests available, you might think that your code is okay, and only at some stage later, you notice that something is wrong. But given that meanwhile, you might have done many things, it will be much harder to identify that change which actually broke your code. So having tests available, using unit testing, is really important here. So I would stress that if you're not familiar with unit testing, read about it, learn about it. It's a really useful thing to know about. And of course, the other thing which you also would really need is version control. So use version control, use Git or whatever version control system you want in order to keep track of your versions. And of course, that also makes it easy to revert. If somehow you introduce a bug, then it's much more easy to get back to a working version of your code, because the history of your changes is there. And by the way, Git actually has a very nice thing, which is called bisect, and which actually, in combination with testing, allows you to automatically find the commit which introduced the bug. So that's something which is pretty neat to know, and which might help you quite a lot when you're developing code and when you're optimizing. So unit testing, version control, really important here. Okay. So if you don't profile, go directly to jail, you don't get any money. Okay. I do want to talk a little bit more about profiling. There is another profiler, and that's a memory profiler. And for some reason, I don't have slides on that. But that's also useful because it will tell you also on a line-by-line version how much memory is used by each line. And that can, of course, be quite convenient in case you are, let's say, somewhat short on memory and you want to figure out where the memory is going. The last Git feature, yes, that would be Git bisect. What I'll also do, it would lead us a bit too far here, but for those of you who are not familiar with testing, let me find and put a link to a repository in the chat. So this talks about many things, but unit testing is here as well. So there are slides to this training. Actually, there is one scheduled for like next week or the week after that. Let me have a look. In case you would want to attend. It's not a praise training, so basically it's a training of our HPC organization. No, this is not the one training at defense. Yeah, here it is. So basically, you can, if you want, you can join that training. It is organized by the Flemish Supercomputing Center, so it is free of charge. It's not a praise training. Let's be clear about that. So, but it might be useful. So feel free to register if you want. Okay. All right. So what I suggest we do is profile something. So just to get some feeling for how it works, I would suggest that you take some source code. You might want to take the example which is in the repository. You might also use an example of your own, which would be even more useful. And I would say try out cProfile and SnakeFish. Okay. So if you don't have any code lying around, just use the repository. Otherwise, I'd suggest using your own code. And just try. See that. All right. So let's spend like 10 minutes on that. And if you have questions, feel free to ask. I'll put the line again, how to profile. Ah, yes, the combating. Yep, sure. I'll probably need to cheat because I always forget, but I have a cheat sheet which tells me how to do that because, yeah, of course, I don't do it every day. Let me go to projects. Okay. I don't have my cheat sheets here. Okay, let's get them. So there is yet another repository, which is quite useful, at least for me. This guy here. So I'm just going to clone that. Yes. Okay, what did I do? Ah, yes, of course. Just update it. Like my key. Okay, and now I can clone. Okay. I was talking about memory profiler. Yes. Yeah. Yes, there is a module for it. I have to look up the name because for some reason it's not in the slides, and I don't remember why I didn't put it in the slides. I must have had a very good reason for that. So I'll talk about it in a minute. Let's first set up the environment, and then we can talk a little bit about creating environment. That's it. So this cheat sheet actually tells you how to do it. So basically, let me. Did that happen? That was not the plan. Okay. So basically, let me just make an environment. So let me go to Python for HPC. Okay. So I've got two environment descriptions. One is the why is this? This is annoying. Okay. So basically, I can use the environment file to create an environment by using conda and create, and then -f with the environment YAML file. Now, if I do that, I'll overwrite my existing environment. So I'm not going to execute this, but this would be the way to do it. All right. So this is one way. The other way, yeah. So we will talk about multi-threading later on. That is a specific subject for tomorrow or Thursday. I don't quite recall the schedule, but we will discuss this in quite some detail. And yes, you will get some speed ups doing that. But as usual, there are quite a number of caveats there, so we have to be a little careful. Okay, so that's the way to create your environment. That's one way. There is also another way, which is using the spec file. Let's have a look at that. So basically, see. Using the spec file, where is it? Should be here. It's not here. Okay, so it's only with the environment file, not with the spec file. The spec file, I'd have to look up how to do it. I don't remember offhand. I usually use the environment file anyway. Okay. Now, about the memory profiler, let's have a look. So this, this, and here I have my Python environment. So don't seem to have it installed. Okay, let's have a look. So Python profiling. Okay. And that would be the package. I'll put it in the chat. Okay. Let's perhaps just install it, then we can run it. It's a while ago that I did this, so Okay. Right, so it's still there. Now I think I can just do memory. No, I'll have to look it up. It's too long ago. Okay, so that basically works the same way. And okay, we just use memory profiler. All right, so let's see what to do. I'm going to write something just to illustrate things. So let's say import that sounds interesting. So invalid elf header typically means that you are likely missing some Windows implementation and a Linux implementation. Are you sure that you are? Which operating system are you on? Okay. I've never seen this before, but basically it means that there's something wrong with the library. Basically, versions are mixed of something. The elf header is typically for libraries and identifies how a library should be loaded. So if that is wrong, it means that some different implementation is being used. So that's a little bit weird. Yeah. And the environment which you're using is the one I created with the env YAML file. What I would suggest, because probably there is a dependency issue there. No, you shouldn't run any install script. What I would suggest is that you just create a fresh environment and just install the packages as you need them. No, again, no. Normally it should just work. So basically just build up your environment as you go. That's probably your best shot here. Normally, I think if memory serves, let's verify. That the environment file, yeah, it's pretty version agnostic actually. So it should normally not give you problems. So I don't know, but I've never worked with OpenSUSE either, so I have no idea. You can just click the link and you will find a button to register for external people. It's a KU Leuven thing, so a specific university registration system, but they allow registrations from a third party. So non-staff and non-student registrations, it's no problem. Normally you can find it. Let's try and go through it. I close the window, I think. Central. Let's go there directly. Let me do that in an incognito window because otherwise it knows me, and that's not what I want. So normally you click the more info button and then you accept all cookies, blah blah, and then you should be able to find the registration button. So basically just choose via phone here, and then you just fill this out and you're done. That's it. But you have to use via phone. The KU Loket thing is for KU staff members and students. Okay, close that. This. The memory usage thing. Yeah, I was writing a script for that. Okay, so let's say ASNP uniform and size 0 minus 1, and size is 5,000 by 5,000. Okay, and then we have B, and that's the same thing. And now on something like C is A2 plus B times B, and then B is C times A power 2, something like that. And then just to make sure that something will happen, we'll compute the sum of all the elements of D. Just make sure that that's something. Okay, so that is our small script, and normally we should be able to use the Python memory profiler. Okay, and we have our script, which is test.py. And then we get a huge number, but we don't get output. I probably have to specify that I actually want to profile something. Okay, I'm afraid I'd have to really have a function for this. Otherwise, it's apparently not going to work. Let's see. Oops. Let's see. Okay. I want to profile this. All my functions. Doing that, I hope I get a decent profile. Yeah, so basically this is what you get. And as you can see, you get the different amounts of memory which are used on each particular line here. Okay. So this can give you some interesting information about how memory is used and how much it increments. And as you can see, there is quite a memory increment here because of these temporary arrays and so on. All right. Okay, everyone succeeded in doing some profiling. Okay. Are there any questions at this point? Okay. So what I would suggest is that those of you who don't have issues or don't have questions, I'd say let's break for lunch, and we can discuss your problem now if you want. Perhaps it's easier if you activate your microphone. Otherwise, you have to do a lot of typing, and that might be inefficient.
Yeah, hello.
Tell me, what's the problem?
I want to, I think I just dropped behind, so I want to create this environment. I will try the same that you mentioned, but it didn't like help me.
Okay. And do you get an error message, or what is happening?
So when I run the terminal, it says that the file didn't find it.
Okay. So you need to be in the top level of the repository. So this is the top level. So you would see this file here,
Okay.
environment level. This is one you need. And then you can do conda env create -f and environment.yaml.
Okay.
But make sure that you're in the right directory. If you don't see this file, it's of course not going to work.
Okay. Okay. I get it. Thanks.
All right, excellent.
Yeah.
This will take a while, and as one of your colleagues suggested, maybe Mamba is a better option. I never experimented with it, but I heard indeed from people that they are quite happy with it. For me, I'm still happy with Conda. It doesn't really annoy me, so that's why I stick with it. But at some point, I'll have a look at Mamba, and I'll also have a look at Conda Forge, just out of curiosity. All right. Does it solve your problem?
Yes, I mean, I will create this environment and then after break, I will ask you about this
Okay.
profile. Okay.
Okay, excellent. Yeah.
Thanks a lot.
All right. Enjoy lunch, and I'll see you at 1. If there are any questions meanwhile, feel free to type them in the chat. No problem. Ah, yes, the snake fisting. Let's have a look. Where am I? Just a second. That doesn't seem very relevant. With this, let's go to this guy here, and I had a profile, I think.
Hello.
Question.
Yeah, but I think your screen is not visible yet. Or not?
Ah, yes, indeed. I'm not sharing my screen. That is a very astute remark.
Oh, thanks.
Yes, that should be better. Thank you. I should also, yes, the recording is still, yeah, that was a bit silly. I should have stopped the recording over lunch, but yeah, then again. Okay, right, so the snake fisting. So I'm just using the profile which I already have. And then this is what you get. So you can either have it in this icicle mode. So basically this is a bit like icicles which drop down from some point, or you can have it in a sunburst mode. Which you use is of course the same thing, it's the same information. It depends a little bit what you prefer. So let's go to the icicle thing. So basically what you see here at the top, that's the entire execution. And then during that execution, stuff happens. So for instance here, this is the module load. And this takes quite some time. Here we have other modules which are loaded. And then normally you should see the name of the function somewhere. Okay, there it is. But this is all system stuff, so that's not so very interesting. What I would like to see is my own code. Let's limit the depth a little bit. That might be more useful. So this is the module itself. That's not so interesting. So that's again module. This is the indexing itself. Index tricks.py, that has to do with the indexing of the profiler itself. Core.py, that's all not very interesting. Init.py, and that is most likely, yeah, that's import lib. So basically what we're looking at here is still importing the libraries. Let's go a little bit further to 5. Then here we still have built-in methods. So this is still the import method. Here we have still import. So all of that is not particularly interesting. So we go still further. Okay. And normally now we should have something That makes sense. This is get code. Okay, so this is not really a nice profile, because basically the profile is mostly about making the profile. So let's do the profile a little differently. Let's see. So we have Python C profile. We have .o. Let's override the existing profile, and then we have right. We have Python version, and we want n to be okay. Rule 0 is correct. Let's this way. Okay, and I don't care about the output, so that goes to all right. Now I hope I wasn't over ambitious, in the sense that I'm not quite sure how long it takes to compute all the primes up to 10 million, especially with this slow Python version. But let's see. So let's now visualize the file. Okay. So this is much more interesting, because now basically we get some useful stuff here. So the primes function itself takes almost the entire time. And now, unfortunately, the problem is that that function doesn't call any other functions. So this is a bit a boring profile, in the sense that the only things it shows is the single function which is called now, which is the primes function in the primes vanilla profile. So, okay, not an ideal example. Let's see, do we have something which is a bit more interesting? Let's see. Performance number puzzle, but that's an IPython thing, so that's not very interesting. Let me go to repository. Okay, and okay, that's also Python. Too many notebooks, not enough stuff to really execute. Something here somewhere. Let's see. Yeah, the problem is I need something with quite a number of Python functions, and most stuff in here is going to be just calls to NumPy, which is not particularly interesting. Okay, let's do this differently because I really need to find a nice example, and I at the moment don't have one handy. So let me think about it and I'll come back to it with a good example to show you a better profile. But I think it was more or less clear how it works. So basically, you get a visual representation of the functions which are called, and that way it is more or less easy to see where you have to optimize. Yeah, I really have to look for a nice example. This thing, is there something which might be interesting? Yeah, but it's also the prime thing. No, this code is not really nice for it since it doesn't show many functions. No problem. I'll find something cute and show you later. Okay, let's continue with this afternoon's topic, and that is number. And number is rather interesting. So what we're building up to here is we're going from quick wins, which we discussed this morning, like num expression and using some Python implementation, which is faster than what you get by default. Two things that require a little bit more work, and number is among these. And as we progress, things get more and more involved in the sense that it will require more and more effort from your side. But Numba is one of the examples where things are still quite easy and you get rather interesting gains with respect to performance. Okay, so what is it? Basically, what you do is very simple. You annotate Python functions with decorators. That's easy. We already did that with the profile decorator for the line profiler and the memory profiler. But here in this case, what happens is that that will instruct Numba to transform your code into C code. So basically, your Python function will be transformed into a C function, one or more C functions. And that is going to be automatic and it's going to be transparent, so you don't notice that. It is a very convenient way of doing this. So for better performance, you need to provide some type information. So basically that the compiler can do a better job. And it can generate code for GPUs as well, but you would have to know some CUDA for that. We'll also discuss this later on. So, of course, there are many ways and many claims that Python can be faster using package XYZ. So there are two things here. One is how much change is required in your code in order to use that specific package. That's basically your investment. And on the other hand, what is the return? So how much efficiency can you actually gain? And that's a question which will return a number of times because we will explore various approaches to speed up your code. And those approaches will require a bit more or a bit less investment, and they will return better or not so good performance. So for instance, in the case of using num expression, we had to modify our code a little bit. Rather than having a numpy expression with operators, we packed that into a string and used ne evaluate rather than doing that directly. But that I would qualify that as a very minor investment. The gains you got depending on the particular function range from 10% to a factor of 20. So yeah, very little investment for Sometimes small gains, but sometimes pretty large gains. So how is it with Numba? Okay, let's do the prime example. So what is the idea? We compute the first n prime numbers and we return those as a list. That's basically the idea. And let's assume we have an implementation. We'll come back to the implementation in a minute, but let's assume we have the implementation. So we have two implementations. One is primes p. In that module, it's a pure function. It's a pure Python implementation. And then there is the module primes n, and that's the Numba implementation. And in both cases, we use timeit, and we compute the first 1,000 prime numbers. And as you can see, the Numba implementation is quite a lot faster than the pure Python implementation. As you can see, the Python implementation requires 3 microseconds, while the Numba implementation requires 200 microseconds. So basically, we get a factor of 50 performance improvement. Okay, so I would say that's definitely a good return. Question is, what do we need to invest? How drastically do we need to change our code in order to gain this factor of 50? All right, let's have a look. So this is the original Python code, and basically it's a recurring example. So basically, I'll go through it briefly. So what we want is an array of the first 1,000, in this case, prime numbers. And basically, we just do that by checking whether a number is prime or not. This is simply done by computing the modulo. If we find a divisor which is not equal to the number itself or 1, then it's not a prime number. So if it's a prime number, we store it. That's basically how it works. So this is actually pretty naive in the sense that, for instance, we go up to k. We could definitely do something more intelligent here, but it doesn't really matter. We're mostly interested in how to speed this up. And then we put the result in the results factor. So if n is a prime number, we're going to store it and we return the list. And this we do for all values of n, and we go up to 1,000 maximum. Okay, so how do we do this in Numba? The code in red is what we added. So basically we did an import and we decorated the function with JIT, which means just-in-time compiler. That's all we needed to do, and the gains which we got were a factor of 50. So that's a fairly impressive return on investment. Since the investment is very low, just 2 lines of code, a factor of 50 is really pretty spectacular. So that's actually very nice. Okay. The question is, does it always work? So one of the things which you notice is that in fact I used NumPy here in order to store p. If you do this in really pure Python, then of course you would have to use the array implementation, which is in the standard library. And that's what I'm using here. So I'm creating an array of 1,000 values which are all 0. And they're created out of a list of 1,000 elements. Okay, so that's just a pretty trivial change in the code. Okay, so what happens when we run that? Well, basically, NA is numba with this array implementation, and PA is just not using numba, so basically just plain the Python thing. So as you can see, now in fact we have a bit of an issue, since actually the numba implementation is in fact a little bit slower, because we have 800 microseconds for the pure Python implementation, and we have 2 milliseconds for the numba implementation. So this is, and actually the factor is wrong, because that would be a factor of 2, almost 3. So that's a little bit weird, but okay. At any rate, the bottom line is that if we use this array implementation, then numba can't really do anything useful here. So basically, it is a little bit tricky when numba works and when it doesn't work. So if you use the array, then you really get a pretty bad performance. Okay, so can we do more impressive things? Well, let's have a look. So we again import the just-in-time compiler as usual, and this function is actually an implementation of computing the Julia set. So the Julia set is a fractal, and we get it by iterating this particular expression here with complex numbers, and we do that up to a maximum number of iterations, or up to the point where the absolute value or the norm of the complex number, as long as it's less than basically 2. That's the idea here. But we keep on iterating. And we do that for a number of points in the domain of complex numbers. Okay, so let's add type information to the just-in-time compiler decorator. So basically, this is the function signature. So what we do is for each argument, we specify its type. So if we look at the function, we have the domain. The domain is complex numbers. Complex 128 is double precision complex values. Why? 128 bits is 2 times 64 bits. A double precision floating point number is 64 bits. So both real and imaginary part do have double precision. Okay. The array notation here, the brackets, mean that this is in fact an array, and in this case a one-dimensional array. Okay. The second argument is iterations, and that just stores for each value in the domain the number of iterations which are computed. And of course, that would have the same dimension as domain. It stores int 32. So basically integers which range from -2 billion to 2 billion, so 32 bits, minus 2 to the power 31 up to 2 to the power 31 minus 1. And it's also an array. Okay. Then we have max norm. That's just a parameter, but it's a floating point parameter, double precision. And maximum iterations is again an int 32. So this is the type information about each argument of our function. And the function is return anything because the results are stored in iterations. So the return type is void. So this is information which will be passed on to the code transformer, which translates the Python code into C code, and that makes the life of that tool a lot easier. So it can generate code which is more efficient. Okay, so that's the function signature specification. And if we do that, so basically the just-in-time compiler versus the eager just-in-time compiler, so with information about the types, you see that we get a 2.4 speed up, which is again a good return on investment because yeah, we only need to specify these types. That's it basically. Okay. So in total, we get a factor of 2000 with respect to pure Python. So that's not bad either. Okay, so we need to know a little bit about the type mapping. And this is easy if you're familiar with C or C++. So basically in Python, we have a number of types. There is the non-type, and that translates to void as a number type. In Python, we have integer, and remember, there is a catch here, because in Python 3, an integer has no upper value. I mean, there is no largest integer which you can represent. You can always add 1 up to the point where you completely fill the memory of your computer, and then of course things start to fail. But apart from that, there is no upper limit. Of course, if you realize that under the hood, Numba is going to use C, then of course you need to translate an integer to a type in C. And you do have quite a lot of choice. So you can have an int 8. That means you use 8 bits, sorry, for an integer. Okay, 8-bit. That means that you can represent values from minus 2 to the power 7 up to 2 to the power 7 minus 1. So from minus 128 up to 127. Int 16, same story, but now you have 16 bits. So basically from minus 15,000 something up to 15,000 something. 32-bit integers is what you typically work with, so that's basically minus 2 billion up to 2 billion. And integer 64, and that's from minus 2 to the power 31 up to 2 to the power 31 minus 1. And so that's really, really huge. Sorry, 2 to the power minus 2 to the power 63 up to 2 to the power 63 minus 1. Okay, so that's huge numbers. Then for each version of integer, you also have an unsigned version. So for example, uint8, that gives you values between 0 and 255. So basically 0 up to 2 to the power, the number of bits, minus 1. And you have that for each type. Okay, why would you care? I mean, why not just, I don't know, int 64 all the time? Who cares? It's large. It will store everything. Well, there is of course a trivial reason, which is that if I can store my information in an int8 or a uint8, okay, that uses 8 times less memory than int64 or uint64. So that would be a fairly trivial advantage. But is there another advantage to using small types? One of the things which is really important to realize when you're writing scientific code is that very often you're actually not so much restricted or your performance is not so much restricted by the number of operations you do per unit of time directly, but much more by the data which you can transfer from RAM, so from your main memory, to the CPU. This is very often your actual bottleneck. So basically that means that the less data, or rather the smaller your data is, the more data you can transfer per unit of time. So if I have an int64, and now we're talking arrays of int64 versus int8, well, for one int64, I can actually transfer 8 int8 values. So my memory bandwidth is used much more efficiently if I use int8. I can transport 8 times as many values. So basically, if my integers, if I'm happy with this kind of precision for my integers, this number of digits for my integers, then of course it's much better to use the smaller ones. And of course we have the same story for float. So for float, basically in Python, that is going to be double precision. Python itself doesn't make a distinction between single and double precision, it's just double precision all the time. In C, you would have float 32 and float 64. Float 64 is 8 byte, that's double precision. That means you get 15 significant digits, and you can represent floating point numbers up to 10 to the power 308. The smallest one which you can represent, which is not equal to 0, would be 10 to the power minus 308. So that's for double precision. For single precision, you have 6 to 7 significant digits, and you can represent numbers up to 2 to the power 38, or smallest number, which is non-zero, 2 to the power minus 38. So again, same thing. Double precision floating point is double the size of single precision floating point. So your effective memory bandwidth will go up by 2 if you use single precision. Is that enough? Well, often it is. Sometimes it's not. If you really need double precision for your computations to be sufficiently precise, then okay, live with it. But otherwise, it's a very good idea to switch to float 32, because that will give you much better usage of your available memory bandwidth. And of course, you can store your data in half the memory. So that's one argument for floating point. The other argument is also, we already discussed factorization. So basically, there are some options which you have. So the question is, can you actually use more efficient numerical types in Python directly without bothering with Numba? The answer is sort of yes, but you would have to use NumPy for it. So in NumPy, you have the same types. Well, you actually have some more than you have here. For integer, it would be the same. You have the same types. For floating point, you have 2 additional types. There is a float 16, which is half precision, and there also is a float 128, which is quad precision. And then for complex, you would have complex 64, complex 128, and complex 256. And of course, if you use these types, then you have the same advantages of using Numba without having to use Numba. So is that using them directly in Python? Nah, not really, because you're using NumPy. But yeah, it's a bit closer to home than using Numba. And of course, if you're using pandas, so if you're in the setting of analyzing data in a data science context or whatever, then again, same story. All the types which I've been discussing here for NumPy are also available for pandas. As far as I know, pandas doesn't have float 16 or float 128. Yeah, float 128 maybe. But at any rate, it does have single precision, double precision, and all the ints you can dream of. So that would typically be the way I'd go in, call it Python. And yeah, I mean, unless you use many integers or you use many floating point values, you really don't care at the end of the day. So typically your data is going to be stored in arrays. If you're using arrays in Python, and it's for numerical computations, you use NumPy anyway. So yeah, I mean, if I'm doing scientific computing in Python, yeah, then it will be NumPy, most likely. And then I do have all these types without any issues. Okay. So for complex numbers, same story. Complex 64, don't get confused. That's 64 bits in total. So that's 32 bits for real, 32 bits for imaginary part. So that's single precision complex. And of course, complex 128 is double precision complex. If you have an array in one dimension, then you use the column notation. The default data types in NumPy. So basically, default types in NumPy. So for floating point, that is double precision. So that would indeed correspond to the one in Python. For integers, it depends. The documentation says if you're on a 32-bit operating system, then the default for NumPy for integers is going to be int32. If you're on a 64-bit operating system, then the default for integers in NumPy is going to be 64-bit. Okay. Except if you're on a 64-bit Windows system and you're using the Windows implementation of Python, then for whatever obscure reason that I completely fail to understand and actually also don't want to know about, the default for NumPy integers is in fact 32 bits. Okay, so bottom line, in any case, if you want to make really, really sure that you are using the data type which you intend, and that's especially important if you rely on the fact that you have 64 bits to store an integer, then specify it explicitly anyway. Don't rely on the default, just specify it as the D type of a NumPy array. That would be my advice in that case. Okay, so one of the things which you should really keep in mind, of course, is that in Python, the integers are not restricted. They can have any value. So basically that means that you can have integers in Python which you cannot map to int64 because there's just more bits required than the 64 which you have in int64. Is that likely to happen? I don't know. I mean, 2 to the power 63 minus 1 or 2 to the power 64 minus 1, that's really, really, really a huge number. Will you ever count up to something that's more than that? Not so likely. So you should be okay with an int64. Okay, so for two-dimensional arrays, we have this notation, which again reminds you a lot of what happens in NumPy. So basically, we use the square bracket notation, and each column represents dimension. Okay. All right. So this is rather cute. With relatively little effort, we can get quite a lot done. Let's perhaps have a look at the notebook. If I can find my notebook, that should be here. Okay, so that's my untitled notebook, and I should move it a little bit. Okay, that's better. All right, let's have a look at source code and Numba. What have we got? So this would be an example of computing Pi. And so this is a different computation. So basically, we're going to use the just-in-time compiler. So we import NGT from Numba. And here we have compute Pi. And we are going to compute Pi by throwing darts. So basically, we have a square board. And in that square board, we insert a circle. And basically, the circle has the same radius as the square side. That's the idea. Well, the diameter is the same as the side of the square. So basically, then we throw darts, and the darts ends up somewhere in the square, but it may or may not end up in the circle. If it ends up in the circle, we count it. If it ends up in a part of the square that does not contain the cycle, then we discard it. We don't count it. And basically, then we can compute Pi by dividing the number of hits by the number of darts which we threw, and we multiply by 4. Okay. So that's very easy. We can do that in Python. We can also do that using the just-in-time compiler and using the just-in-time compiler, but with type information. So basically, I need to this, and then this, and then this, and then this. So basically, the types here, we have the number of tries, and I just use an int64 for it. And the result, of course, is a value of pi, so that should be float 64. Notice that the signature here is slightly different from the one in the slides. So basically what I'm providing is a list of strings. And this is basically the signature of one implementation of this function. So this implies that I can actually create multiple implementations with different signatures. So that is possible with okay, so we can run this. I'm going to run all 3 of them. And then you see that for the pure Python version, it takes 27 milliseconds. For the just-in-time version, it takes 690 microseconds. And actually, there is no difference. Providing type information or not doesn't help. And I'm throwing 100,000 darts. So basically, quite a number of them. You can increase that if you want. You would see very similar behavior. So here, providing the type information really doesn't make any difference. But as you can see, using Numba has actually sped up our computation by a factor of 40 approximately. So that's rather nice. Okay. This would be the example of the Julia set. This is interesting. So I have, okay. So these are Python scripts. So this would be an eager script. So again, with the type information, notice this is the older notation. So basically we could replace this by using the same notation as we did before. So as a list of strings, but here it's the old type notation. So basically these here would run the scripts. And here, this is just to initialize and to run the thing depending on the implementation. Okay. The not just in time, well, the NGT thing, that's Numba just in time. It's that would be the more modern implementation. So basically, the signature of the decorator is different, and it's very strongly encouraged to use the new one. So that's basically the intuition. So there's nothing very odd here. It's basically just the recommended way to do things right now. That's essentially the bottom line. Okay. Right. What else can we do with Numba? Well, there is more to be done with that. It's useful for more things, and that's for ufuncs. Okay, so what's a ufunc? Well, you know ufuncs. You might not realize, but you actually know them, because if you use NumPy, you actually use ufuncs, and that's basically a function which operates on an array as a whole. That's the idea. So, for instance, the np square root function is an example of a ufunc. You can also do reductions. So, for instance, a sum or a mean is also a ufunc. So, essentially, any function that operates on a NumPy array as a whole, that's a ufunc. Okay, so you can write them in C or Python, but frankly, that is pretty cumbersome. It's quite a lot of code. It's quite a lot of boilerplate code. It is annoying. So Numba has a very nice way of kind of automatically generate ufuncs by using the vectorize and the GU vectorize decorators on functions. So basically, let's have an example, and let's write the Julia set function as a ufunc, because at the end of the day, remember what happens. We have some array of complex numbers, and to each element of that array, we apply the same kind of computation. We will compute this while loop, and we will count the number of iterations up to the point where either we reach the maximum number of iterations or the norm of the complex number is larger than 2. That's basically the idea. Okay. So we can kind of rewrite this into a ufunc, because we can view this as a function from the domain to the number of iterations. So what do we need to change? Well, one of the things which we need to change if we use GU vectorize, so the general ufunc vectorize thing, is that in fact the output array has to be the last element, it has to be the last argument of our function. So domain is the input array, iterations is the output array. That's the idea. The array that this function is actually going to return. Okay, so the GU vectorize signature of the decorator is much the same. We have a list with the type information, and nothing much changes, except of course that this int 32, which used to be the second argument, is now the last argument. That's just because we need to have that. That's the convention in GU vectorize. That's one change. Two other changes are that the max norm and max iterators now also are vectors. This is because of broadcasting. So basically, depending on the array which we input, we actually need here an array as well. And that is going to be all handled by GU vectorize, but we need to specify it. And then the last thing which we need to do is to add this type of signature. So basically that means that the dimension of the first argument, which is our domain, and the dimension of the output is going to be the same. So this is n map to n. While these two arguments, so basically the max norm and the max iterations, they do not depend on the size of n. So domain is going to be the input, iterations is going to be the output, so those dimensions are linked. Okay. Of course, we need to remember that we have to initialize iterations now, and since now max iterations and max norm are vectors, we have to specify that we want the first element, so basically index 0. Okay, and that's nice because that gives us a pretty huge speed up with respect to Python, in this case a factor of more than 1600. So if you would omit this 0 here, so the index 0, your code would work, but it would be pretty slow. So that would be a problem. And then you can call the Julia set function on any array which you have, and it would produce the array iterations. So although this function takes 4 arguments and doesn't return anything, by convention, it will actually take only the first n-1 arguments, so in this case 3, and it will return the array which is the last argument. So that is a little bit confusing, since it seems that the function signature and the actual usage of the function are different, but that's just due to convention of how GU vectorize works. Okay. And then the nice thing is, if these things are 2D arrays, then you'll get automatic broadcasting. So I could use a matrix for domain, and I would get the matrix with the same dimensions as iterations. Okay. So that's actually pretty cute. So basically, Numba has quite a number of advantages. It's pretty easy to use, and you get very often quite nice speedups. And it's very easy to create NumPy ufuncs, which used to be quite horrible in the past without Numba. Well, it's still quite horrible if you don't use Numba. Okay. So basically, I would say it's definitely worth to try out whether Numba is going to help you or not, since it's really, really cheap. And of course, in the past, and now I'm thinking 5 to 10 years ago, using Numba would be annoying, since it meant that Numba had to be installed on the system where you wanted to run your application, and installing Numba been there, done that, was not really easy. But of course, nowadays with package managers such as Conda and Mamba and name your favorite, basically it's very easy. So all the restrictions which we had in the past and which we took into account, like, okay, yeah, annoying modules have to be installed and the packages are hard to build and people will not be able to run it because of the dependencies. All that actually has gone away with Conda environments. Oh, well, with environments in general, Python environments in general. So the main counter argument no longer applies. Okay. So another thing which you can do is doing NumPy with multi-threading. And this is something which we will come back to later, but we can already have a look at it if you want. So what is multi-threading? Because the term has been used a couple of times, and most likely you're familiar with it, but okay, nevertheless, let's go over it. So if you look at modern CPU design, let me perhaps pull up a slide which makes that a little easier to discuss. Let's see, where do I want to be? I want to be here, but not on the desktop. I want to be here and here and GitHub and code optimization and this guy here. Okay, and I want to move to this slide. Okay, let's use this slide. Damn, that was stupid. Okay, so basically, if you look at hardware, modern hardware, okay, this is not so extremely modern hardware, but still okayish. So basically, if you look at your typical laptop or desktop, you will have a single CPU, so a single central processing unit, and that will, of course, do the work. But that single CPU, in fact, has multiple cores. And typically on your laptop, that will be 2 cores, 4 cores, or if you spend a lot of money, maybe 6 or 8 cores, depending on how much money you spend on it. That means that you actually can do multiple things simultaneously on that computer, independent of one another, because each core can execute a thread, so can basically execute a single series of instructions that make up an application or part of an application. And if you have 4 cores, that means that 4 of such threads can be run independently and concurrently. So that's kind of nice. And of course, if your application is able to exploit that hardware, then of course things are sped up considerably. And of course, lots of software on your laptop is going to use multiple cores. For instance, if you have an email application, you can read your email while in the background the email program checks whether there's a new mail for you. And if so, it will pop up a dialog saying, hey, there's new mail or whatever. And these things happen independently. So you have one application and multiple threads belonging to that application are running concurrently. One thread is going to, every, say, minute, check whether there's a new mail. Another thread is going to update your screen. So basically, if you click on an email, it's going to display that email. or if you click on a folder, it's going to display the list of emails in that folder, and so on and so on. So an application consists of one or more threads. Okay, so if your application can do its computations using multiple threads, and you have hardware that can run multiple threads simultaneously, then of course your application is going to run faster. Do we care? Yeah, we do care, because that really improves the, let's say, the user experience for graphical user applications. So that's nice. Of course, we also care quite a lot in the context of high performance computing, because for high performance computing, we are not talking about 2 or 4 cores. We are talking about many more cores. So for instance, this slide here, that's for a fairly old system, HPC system, where each CPU had 10 cores. And on HPC systems, actually, typically you don't have one CPU, you have 2 CPUs. So in this particular case, a compute node would have 2 times 10 cores, which is kind of nice. That's a total of 20 cores. Of course, nowadays this is, well, pretty old, pretty slow, because typically if you have an AMD system, you might end up with 2 times 64 cores, so 128 cores per node. If you have a very modern Intel system, you would probably have something like 64 cores, 2 times 32, something like that. Typically, Intel has less cores, but they typically perform a bit better than those of AMD, so they're more or less on par. But anyway, you have a lot of cores on a single compute node. So if you can use them efficiently, that means that you get a significant speed up of your application. At most, you get n times, well, the number of cores times the performance which you have on a single core. Okay, that's of course an ideal case, and we will discuss that a little bit later. Yes, those are all physical cores. So that's a very good question, because Intel has the concept of hyperthreading, and AMD has a similar concept. So basically that means hyperthreading means that the computer is going to show you twice the number of physical cores. And I can actually show you. Let me do that using the task manager. Now, how do I start a task manager on this thing? My interface changed a little bit. Let me do it this way. So basically, this is my Windows Task Manager. Nobody cares, but they changed this. Yeah, I have the insiders built and they changed things. So let's see, would that be performance? Yes, it's likely to be performance. So basically, if you look at something, no, that's not here. Yeah, here it is, 8. So basically, it says 8 cores, and that's indeed the hardware cores. So I've got 8, but I get logical processors 16. So basically, that means I do have 8 cores, but each core can actually execute 2 threads simultaneously. Okay, so that means that on an 8-core machine using hyperthreading, I can actually run 16 threads in parallel. Yeah, almost. Problem is that if you look at how this is implemented, then you will see that that means that in the core, certain hardware is duplicated. For instance, the hardware which is used to execute branches, so to do if statements, which also means the looping and so on. So basically your control flow is duplicated. So that's nice. Okay. What else is duplicated? The hardware for dealing with integers, so integer computations. Each thread can independently and simultaneously do integer operations, control flow operations. Nice. Okay. However, what is not duplicated? Well, the hardware which is required for floating point operations. So basically that means that if you have two threads and they run on the same core and they are both floating point intensive, so they do a lot of floating point operations, that is too bad because they can't do that simultaneously. So that means that while one thread is doing floating point computations, the other thread is going to have to wait. Okay, is that a problem? Yes, because that will actually mean that your computation is going to be less efficient than if you just used a single thread on that core. And that's why typically on HPC systems you will see that you can run only as many threads as there are physical cores in the system. So if I would show you this on an HPC system, it would actually have the number of cores equal to the number of logical processes, due to the fact that floating point hardware is not doubled in the core. Might change in the future, but at the moment that is not really working. So that means that for certain workloads, and unfortunately for many scientific applications, hyperthreading is not a good idea. It's a very good idea for user interface applications, for instance. Very good. I would hate not to have it. But for scientific computations, nah, I don't think so. Okay. Let's keep that slide around. It might turn out to be useful later on. Okay. So that's very nice, very good. A few drawbacks of Numba. Well, it's a black box. You really don't have a clue what it's doing. And sometimes there are weird things. Like, for instance, the array example which I showed you. Why do you get really crappy performance if you use an array? And you get really good performance if you use NumPy arrays? Well, if you look at the generated C code, you might find out. But yeah, that's the only thing you can do. You can try the version, see what performance you get, either be happy with it or not. If you're not happy, you should look further. And then maybe you will see, yeah, but here the array thing takes a long time. Maybe I should do something else. But there is not really a way of finding that out, except for looking at the generated C code. Now, if you ever looked at generated code, by whatever is generated, you are probably aware that that is typically very hard to read. So, not so easy. Okay. It has a number of interesting features which are not covered in the slides, but which we will talk about. And one of them is automatic parallelization, which is why I went to this slide in the first place. So let's go back to the notebook and have a look here. So can we do things in parallel? So we again import stuff. Okay. And we define our functions. So nothing special is happening here, this we already know about. But this is the floating, what is happening here. Okay. It's unhappy for some reason. Why is it unhappy? Okay. Random is not defined. Okay, that's interesting. And where do I use random? Ah, here I use random. And indeed, I don't import this. Okay. This is weird. So import. Happy to do that. Okay, is it happy now? Okay, so basically, yeah, I think there is nothing really new here. So this should actually give us the same results as before. Okay, let's not do that. Of course, we can compute pi in different ways. So this was again the throwing darts thing at a square board. We can also compute pi as the result of computing an integral. So basically a quadrature. And we would have to compute this one, and that would give us pi divided by 2. So we compute the integral from -1 to 1 of the function 1 minus x squared. Okay, so we can do that using the just-in-time compiler, and then we can actually specify the thread layer. So we use the config thing. Where's the config thing coming from? Let's have a look. That's here. So we also import config. So that's our configuration. And we are going to specify that the threading layer is OpenMP. We could also choose TBB here, and probably also threads. Okay, so now we have our same function. So nothing changes from this implementation to that implementation, except that we have parallel is true. Okay. And we can also just have the NumPy implementation. So let's run that. Okay, and as you can see, I do get a speed up. It's not really very impressive in the sense that we went from 390 milliseconds down to 280. So yeah, okay, it's a speed up. But if you remember Task Manager, we keep this thing open. While we're executing this. So as you can see, we get a peak here, but this is very short. So basically, if I wanted to get a bit better performance, we can perhaps add a factor of 10. Should still work without too many problems, I think. So as you can see, there is quite some inefficiency here, because as you can see, my CPU goes to 100%, but then it decides to do other things, and basically I don't get that much parallelization. So let's do the same thing now, but using a single core. Yeah, there is some overhead here because of the time it, which of course you have a number of loops, and there are quite a number of loops here. But still, it should be a little bit better, because in total you have 3 seconds runtime. So it should be a little bit better than this. And that's, of course, one of the drawbacks. You really don't have a clue what it's doing. But again, the ratio between the two numbers is more or less the same. So we go from 4 seconds to 3 seconds. Given that this is an 8-core machine with 8 physical cores, this is a very bad parallel efficiency. It's really, really crappy. So yeah, this is somewhat subpar. I'd hope for much better. I don't get much better. So yeah, this is a bit disappointing. Yep, true. There is something nice, by the way, which kind of, sort of, gives you that. I don't know whether you're familiar with Compiler Explorer. Let me show you briefly. I'll probably have to accept. Yeah, of course. Yeah. Okay, so this is something that is really, really nice. It's an extremely nice tool. Let me URL in the chat. So what does this do? Basically, it translates from, in this case, C or C++ code to machine instructions. Okay, that's really, really nice, because it allows you to see what C compilers, C++ compilers, Fortran compilers are doing. But in fact, you can also use it to deal with Python. Let's see, let me close this. Let me add source editor, and wait, how do I do that? I do want to type my code here. I'm happy to do that, but what I want is, that was what I was looking for. So what I want is, okay, yes. So this is good. It immediately, okay, I don't know why it did this function, but it doesn't matter. Okay, so now what I can do is, at least I hope, source editor compiler, yeah, okay, and now it shows me all the instructions for the Python virtual machine thing. So if you are curious about what your Python code is in fact doing, you can use Compiler Explorer in order to figure that out. And that might help you find some bottlenecks, find some weird behavior, because things are not what you expect. So that's a useful thing to know. For, yeah, basically, I mostly use it for C++ and for Fortran. Not so much for Python, because I'm not really, really familiar with the Python virtual machine, but it is quite useful, especially for the other programming languages where I'm more familiar with the machine instructions. Okay, so yeah, I'm not happy, that's for sure, but we can do different things. Yeah, the threading layer, we know that that's OpenMP. Let's use TBB. So basically, what's the difference? Well, in high-performance computing, we need to do multi-threading. And typically, you write your code in C, C++, or Fortran. And let's say up to 10 years ago, if you wanted to write multi-threaded code for scientific computing, you would use OpenMP. And OpenMP is in fact rather nice, because it is a little bit similar to Python decorators. So basically you annotate your code with pargas, so compiler instructions, and the compiler will automatically generate code that executes in parallel for you. So that's kind of very neat. And OpenMP was the default go-to in order to get that done. However, OpenMP is nice, but it has its limitations. And so basically, a while ago, in 2006, there were some experiments to do things differently. And there's a whole history behind that, but at some point, Intel actually acquired a company, a startup company, and created a product which is called TBB, Threading Building Blocks. And at the time, it was Intel proprietary software, so you could only have it if you had a license of the Intel compiler. But since then, they open sourced it, and now you can use TBB regardless of whether you use Intel compilers or not. So if you look at the history of OpenMP, it was mainly intended to parallelize loops. And then later on, in later versions of OpenMP, you got some task parallelism. TBB, on the other hand, puts tasks first, and loop parallelism is just task parallelism. So it's different. It's somewhat different point of view, and that ensures that code that is written with TBB is actually more easy to manage parallelism at different levels with. So that's the main selling point of threading building blocks. And you can use TBB as a backend here as well. So let's try that. And let's do the same thing. So basically, you see we get 240 microseconds. And let's perhaps also do a billion here since that was the last number which we computed with. More. So we should get 3 seconds if memory serves. That was with OpenMP. And so with TBB, we might get a little less. .64. So it's a little bit better. It's still not spectacularly good. Yeah, that's weird. Why do I get OMP? Okay, that is bizarre. I would have expected TBB. For some reason, I still get OMP. Strange. Anyway, so basically, as you can see, TBB does a little bit better than OpenMP, but still it's not really, really good. So yeah, you can use this, but it really doesn't make any sense to run this application on, let's say, more than 2 cores. Because otherwise your parallel efficiency is going to be very, very low, and you're going to make people very unhappy. Let me perhaps talk a little bit about that as well, because that should be in this slide deck somewhere. Maybe it's good to talk about that for a second, because that is also something that's very important in high performance computing, and something that not everyone knows. Okay, so let's talk a little bit about scaling. What do we mean with scaling? Basically, it means how much does my performance improve if I use more hardware. Okay. Now, you can view this in 2 dimensions. One dimension is, okay, I'm going to solve the same problem. So the exact same number of particles, the exact same set of equations, whatever. And I'm just going to use more resources. So I'm going to use more cores. I'm going to use more nodes to solve it. That's called strong scaling. Okay, but there's a different notion as well. You can also solve a larger problem by using more resources. For instance, I want double the number of particles of my original simulation, but I'm going to use twice the hardware. That would be weak scaling. So both of them are important in scientific computing, and actually weak scaling is very often pragmatically more important. Okay, so what do you hope for? Basically, for strong scaling, you hope that the execution time is going to halve if you use double the number of processes. So if you use double the number of cores, for instance. Question is that going to happen? Maybe. So for weak scaling, you would expect the execution time to be constant if you double the system size and you double the number of processes. That's basically the idea. Now, there are a number of ways to quantify how fast or how efficient your parallel code is. Okay? So, a measure which is often used is the parallel speedup. And the speedup for n processes. And that's basically just the time it takes using a single core versus the time it takes to do the same thing, but with n cores. And of course, ideally, you get a speed up of n if you use n processes. In other words, suppose I have a single core efficiency, I have a single core wall time of 5 seconds. If I use 2 cores, I'd hope to have 2.5 seconds. That's the idea. Okay. But there is also parallel efficiency. And basically, that is just the parallel speedup divided by the number of cores. And that basically means that ideally you have an efficiency of 1. So the efficiency typically is a number between 0 and 1. The speedup is a number between 1 and something, and n typically. Okay. Why do we care? So there is a problem with strong scaling. It's not going to scale because some parts of your application can't be parallelized at all, or you can't do it efficiently. Okay, but that implies limitations. So you can split the time it takes with a single core into 2 parts. The time which is inherently sequential, which means that part cannot be optimized, cannot be parallelized, and the time it takes to the time of the part of the code that can be parallelized. Okay. But of course, if we have the time for n using n cores, then TS is unchanged, because whether we run it on 5 cores or on 1, TS is always going to be the same. But TP, ideally, can be divided by n. So Tn is Ts plus Tp divided by n. Okay, now we can compute the speedup. The speedup is Ts plus Tp, that's T1, divided by Tn, so Ts plus Tp divided by n. And basically that means that even if n goes to infinity, you actually have a limit which is Ts plus Tp divided by Ts. So in other words, the fraction of the code which cannot be parallelized is going to put a strict upper limit to the speedup which you can get. So this is a very simple mathematical reasoning that shows that you have a maximum speedup in any case for strong scaling. And that's actually Amdahl's law. It's a famous law in HPC. Okay, that's a bummer. So let's have a look at some numbers. Suppose that the serial fraction is 0.1, so 10%. Then we have the blue curve here, this one with the diamonds. And you see that it starts to saturate pretty rapidly. Ideal, we would have the straight line here with the crosses. Okay, but even for 1% serial code, you'd still get something which is very suboptimal. And you even see for 1000 serial code, you see still the difference. And that's just for, in this particular case, that would be 64. So this is probably 128 cores. And of course, 128 cores, that's not much. That's what you have on a single compute node nowadays. So if you run such an application on 100 nodes, that would mean that you have 12,800 cores. And then, of course, even this guy here, which is now pretty close to ideal, is going to flatten out, and you would get suboptimal results. So Amdahl's law says that strong scaling doesn't happen. You can't do it. It's just mathematically not possible. Okay. So basically the limit for the efficiency is 0. Your efficiency really goes to 0 if n goes to infinity. And that's without taking overhead into account, because there is also overhead, for instance, due to shared resources. Communication takes time. So if you send something over the network, if you use the memory channels, you have a finite bandwidth and you have non-zero latency. All that ends up, if two processes compete for the same resources, that's going to induce overhead. So basically, you are going to be in trouble, and in practice, it's worse. So the red curve would just be Amdahl's law. In practice, you will have something that probably goes down after a while. So your speed up is going to decrease at a certain point. So that's pretty unpleasant. All right, so that is reality. There's nothing to do about this. So if we have this kind of plot, we have the speed up here. What's the ideal number of processes which we would use? What would you pick here based on the speed up? 16, 32, maybe 64. So we have one vote for 16. (32), 32, 24, 2. Okay, interesting. All right. So your opinions kind of are bipolar. On the one hand, we have 2, and on the other hand, we have something between 16 and 32, whatever it is. Okay, so indeed, the problem is if you look at speed up, that's not a really good measure. What you can better look at is the efficiency. So basically, this is the efficiency. And you see that it is dropping. And for 16, we would be at an efficiency of less than 40%. For 32, we would be at 20%. This is really, really, really low. So if you would submit a project for our tier 1 infrastructure in Flanders, and you would say, okay, I'm going to run this, and I want to run this at 32 cores, the board who evaluates this request would say, nah, go away. You're not going to get that project because the parallel efficiency at which you're planned to run this is really, really way too low. 20% is really not acceptable. Even 40%, not really. So you would have to have a very good argument in order to say, well, like, okay, I really want to run this with 16%, and yes, I know it's only 40%, but still I want to do it for these and these and these reasons. So indeed, with two processes, we would have an efficiency of 90%, which is very reasonable. You could perhaps even go to 4 cores, then you have an efficiency of 75%, which is sort of okay. So basically, depending on some other things, you would either pick 2 or 4 cores to run this on. So this is somewhat counterintuitive. Now, of course, there is one single argument to say, okay, I am going to use 32 cores, and that's a hard execution time limit. So basically, if I need my computation done in a given time interval, I might have to might have to go for a low efficiency. Might be. Another reason to perhaps go to a large number of processes anyway is memory requirements, because it might be that I need so much memory that actually I need the associated nodes and hence still have to have quite a number of processes in order to get all my data stored. So that's another potential argument to choose larger core counts or process counts than the sweet spot with respect to efficiency. Okay, let's perhaps just continue this. So that was strong scaling, but there's also weak scaling. And in fact, weak scaling works typically much better. So if you have a system of size n, and now n could be a number of particles or a number of partial differential equations or whatever. So as before, we have the same division ts plus p, but now, of course, ts is independent of n, but tp is proportional to n. So basically that means if we choose the number of processes to be proportional to the size of the system, and that was what we were going to do with weak scaling, we were going to double the problem size, and we were going to double the number of processes. So that's okay. This depends on n linearly, that depends on n linearly. So then basically, if we do the math, we get that the speed up can actually be n. Need not be, but could be. The definition of efficiency is the speed up divided by n. So basically the time it takes on a single core divided by n times the time it takes on n cores. That's the definition of efficiency. Speed up divided by n, essentially. Okay, so now actually we do have potential for ideal speed up, and that's Gustafson's law. So basically, if I double the resources and I double my system size, the time remains constant. That's basically the idea. Okay. So yeah, that's a little bit about scaling in the context of scientific computing. All right. And that's typically nice because, yeah, typically you want more particles, you want larger systems and so on. So that's kind of what you want. And it's good that we have Gustafson's law because we get what we want. All right. Okay, throughput computing, let's not go there for now. I don't care at the moment. Okay. Right, I realized that I forgot to give you a break. Okay, we can do two things. Either you get a break now, let's say 5 minutes, and then we continue for, let's say, another 20. or we just skip the break and stop a little bit early, like for instance 5 to 3, something like that. What would you prefer? No break. Okay. Anyone who really wants a break? Skip a break. Yep. Okay. Great. So we're going to do that. All right. So yeah, parallel processing, NUMBA, I don't think so. But we'll come back to parallel processing later, and we will actually do 2 things about parallel processing. So on the one hand, we will talk about multi-threading, so multi-processing. So that's something we will definitely do. And we will also talk about parallel processing with MPI. So that's for later. NUMBA, yeah, well, I don't think so. Okay. What else can we do with NUMBA? Well, we can do some other things which are cute, and those other things are GPU computing. So let me find the code. That should not be here. That is GPU, sounds promising. And NUMBA GPU, yeah. What is this thing? Section. Okay, no idea what that is. Never mind. This is what I was looking for. So we can actually use NUMBA in order to do GPU computing as well. And that's kind of neat. Again, a slight digression with respect to my system and potentially your system. So this morning I told you, yeah, okay, I'm using Windows 11, and either I use a virtual machine, VirtualBox or VMware, or I'm using WSL. Okay. Now, this is a rather nice desktop system. I already showed you the task manager, so it has quite a big, quite a nice processor, but it also has a GPU, which is here somewhere. Where's my GPU? Here it is. And it's actually a CUDA capable GPU, as you can see. So that's kind of neat, kind of cute, very nice. How am I going to use it? If I want to do GPU computing, how do I get that done on a Windows machine? Okay. In theory, you could install a Windows development something environment that supports GPUs. And if you read a little bit, then people say, oh, don't bother. It's really a pain in the summer and it's not going to work properly, which I'm willing to believe. However, what is a major drawback of virtual machines on Windows and whatever is that you cannot access your GPU. So doing GPU computing from within a virtual machine, be it VirtualBox, be it VMware, forget it. How do you know that your GPU supports CUDA? Very easy. Is it NVIDIA? Then the answer is yes. If it is an AMD thing, then the answer is no. So typically, if you have an NVIDIA GPU, it's going to support GPU computing, but not everything is supported. So for instance, the GPU which I have is an RTX 2050, I think, if memory serves, don't remember. So it supports CUDA. It's a RTX 2060 actually, but okay. So it supports CUDA, but it doesn't support every feature. So basically, what it will not support is double precision arithmetic. It's only going to compute single precision. That's one of the limitations. Another limitation is that it is not going to check memory. So basically, if something goes wrong in the memory, nobody knows. The computation will just be wrong and it will not be flagged. So that's 2 drawbacks which you have. if you have, let's say, RTX class GPUs. So those are the GPUs which are intended for gamers on the one hand, and for people doing, let's say, not really professional graphics. So if you really do professional graphics, then you use, what are they called? Quadros. Yes, thank you. Exactly. That was the word I was looking for. So basically, that is what you would put in a desktop machine, which is really intended for video processing or for heavy-duty professional photo editing, things like that. They cost lots of money. And then, of course, for real computing, you have the series of GPUs which are intended just for that purpose. For instance, the latest ones are the Ampères, which are really fast. You have the V100 series, the P100 series, and so on. So basically, that would be the choice which a compute center makes. So in our HPC infrastructure, we have a mixture of P100s and V100s, and at the tier 1 level, we have a number of A100s. So that's what you would do in a compute center. Okay, so in WSL2, indeed, you can in fact install CUDA, and that's what I've done here as well. So that's a choice you have to make. If you want GPU computing on Windows and you want to run Linux, you would have to use WSL2. You just don't have a choice. Virtual machines are not going to do it. Neither VirtualBox nor VMware. They don't talk directly to your GPU. Unfortunately, but that's the problem. And that's also why I have this WSL2 thing, because otherwise I can't do GPU computing. And indeed, there are various ways to install it. I frankly don't know what the Lambda stack is, so I don't know what that is. I just used the instructions which NVIDIA makes available. So it's some doing, but yeah, that's indeed the install guide, exactly. Yeah. Now there are two things. You have a CUDA capable GPU or you don't. If you don't, yeah, that's where the story ends on your own hardware. What you can do is switch to Google Colab. So Google Colab is a service offered by Google. It allows you to run notebooks. They're very like Jupyter notebooks. There are some small differences, but they're more or less the same. And you get a virtual environment which can have a GPU. And if you're very adventurous, they also have TPUs available. So the tensor processing unit, which is hardware that is developed by Google itself. I never experimented with it. Yeah, time is something that is finite, so I never got around to it, and we're not going to buy TPUs in our HPC infrastructure anyway. So yeah, okay. There are some HPC centers which do have TPUs. If memory serves, Barcelona has them. So basically, if you have an account on Mare Nostrum, then you maybe can access them. Okay, so this is just going to be GPUs, and so basically I'm going to, oh there, something goes wrong. Module named Matplotlib. Oh, that's interesting. Why? That is bizarre. Okay, that should be easy to fix. This is weird. Okay, let's have a look. So, what's going on here? Okay, so let's provide see. then let's list. Okay, something obvious on here. Yeah, interesting. Conda crashed. Okay, great. Okay, deactivate. Deactivate. Okay. Matplotlib inline, interesting, but no other Matplotlib stuff. So okay, Conda install. Yep. Now I am getting a little suspicious. It might be that I need to load another environment, but let's see. Yeah, seems to work. Okay. So as you can see, I do import number stuff. One of the things I'm importing is CUDA, and also from CUDA random, I import some stuff. Because if you want to do random numbers on a GPU, you actually need some libraries for that. Okay, so this is just a Gaussian function, and it is going to do some computations. So basically, nothing special. Okay. So this would be NumPy, essentially. Sorry, this is not NumPy. This is just pure Python functions. And for some reason, it takes forever. Okay, so basically almost 5 seconds. We can vectorize this and time it again. Okay, so well, lots faster, 7 milliseconds. So this is a huge speed up. Okay, so this was just using vectorize as before. So now we are going to use vectorize, but with target CUDA. So this means we're going to create CUDA code. Okay, and if we time that, things go wrong. What's going on? CUDA support error. A driver init. Oh damn. No device. Yeah, that's nice. That probably means I need a different environment here. Let us check. So GPU. Do I have a different environment? There is a lot of stuff here, but no specific environment that I can see. Okay, probably this broke due to some updates somewhere, so I'd have to figure out what is going on, and that is likely going to take me a second. Let's look. Do I have a specific environment for that? Yeah, I have a CUDA environment. Let's Conda deactivate. And Conda activate wrong. Deviate. Failed to create symbolic link. Yeah, okay, that's fine. I don't mind this. Then let's try. Okay. And let's open number. And let's see whether this is better. Okay. Promising. And that, of course, still takes forever. Well, 5 seconds times the number of executions. Okay. All right, and now this looks better, and that also failed. Okay, again, no device. However, I had this symbolic link thing, so I might have to set the symbolic link myself. That is probably what's going on here, but I'd have to figure that out. Okay, let's just assume for now that this works. Basically, you see that it's quite easy to generate CUDA code. You just have to specify the target, and then basically things automatically work, unless they don't. So basically, here, this is not going to work because I need to fiddle with my system. If you update stuff, stuff breaks. And I should have tried this before, but I'll fix it in a minute, and then I can try again. Okay, so basically, well, apart from the failed demo with CUDA and NumPy, that was what I wanted to tell you about Numba. So I think it's pretty useful and nice to at least try, especially given the fact that it's nowadays very easy to use using package managers. Are there any questions about this? Meanwhile, I'm quitting this so that I can try and fix the linking thing. Why does this thing not listen to me? Okay. Okay, so indeed, there is no libcuda here, which is a problem. So what I need to do Okay, where was my lib CUDA originally? Lib CUDA. Which doesn't seem to be there. So where did I hide this? Where? Here? Interesting. That looks promising. That is likely the one which I want. So I think between this guy and okay, and now see, with some luck, something intelligent happens. Okay. Right, so I want my function definitions. I don't want to time this, I already know it takes a long time, so I don't care. Okay, vectorization, and now the GPU timing thing. Haha, it works. Isn't that brilliant? Okay, and as you can see, I get 5 milliseconds rather than 7.5. So it's a little bit faster, but again, not hugely so. So this is not that intensive on the GPU. It's not surprising that the performance is not really astounding with respect to the CPU. Also take into account the CPU characteristics on this system are in fact pretty heavy, in the sense that if you look at the performance characteristics of the CPU, you see that it's a 4 gigahertz CPU. So yeah, it really has some punch here. So you really need something that really runs well on a GPU in order to actually gain from it with respect to a CPU such as this one. All right, so fixed the problem, great. Any questions? If not, I would suggest that you try some things out. For instance, a very interesting exercise would be to port the Julia code to the GPU using Numba. Should be fairly easy. In the slides, you have the code for the CPU. You know how to adapt it to GPU. I mean, that's very straightforward. You just add target CUDA, and you can try how the performance differs with respect to what you had before or what you have on the CPU. Okay. Okay, interesting. So that's data science stuff. All right. I'll definitely have a look at it. It's always interesting to know. Okay, so if there are no further questions, I'll see you tomorrow at 10, and then we continue with Cython, I think, if memory serves. So I would like to do a very quick poll. That would be interesting. Yeah, so the recording for today's lecture, I'm happy to make it available. Let's maybe put it this way. Is there anyone who objects to publicly share the recordings? If so, put it in the chat. Or tell me by audio. If no one objects, I'll put the recording publicly on YouTube, and I'll put the link in the, well, okay, no, I don't need to. Yeah, it's true. I don't need to do that. I can still have it unlisted, so there's no problem with respect to GDPR, and I'll put the link in the Google Docs document. So everyone who has access to the document can also access the YouTube video without any issues. It will take a while before it's there, because Blackboard takes a while to process that video. Then I have to upload it to YouTube. YouTube also takes a while to process, so that's going to take something like 3 hours total, at least. That's a little bit unfortunate, but that's how things work. I might also have a look into skipping Blackboard. Skipping YouTube and making it publicly available on Blackboard. I think I can also do that, and that would avoid the upload step, which takes quite a while because the processing on Google is on YouTube is fairly slow. Okay, a quick poll. Oh. All right. Okay, so basically, most of you, yeah, no problem, you're done anyway. So I'll see you tomorrow. So most of you are familiar with C and C++, which is very good. Some of you only Fortran, and one of you with none of those. Okay, I'll take it into account. So no problem, I'll show you the results. The poll, so basically that's the That's more or less the tally. Okay, no problem. We'll deal with it. It won't be an issue. Okay, excellent. So, unless there are any more questions, I'll see you tomorrow. If there are questions, feel free to type them in the chat. You can also always email me, no problem. So yeah, just let me know. All right, see you tomorrow.